Here we have a 2,000-pound elevator decelerating from a speed of 25 feet per second down to a stop in a distance of 50 feet. We're interested in determining the deceleration, and then in the second part of the problem we want to know what is the tension in the cable supporting the elevator for this situation. So let's first do a little bit of kinematics. Initially we have a let's see, where is my color here? Here. Initially we have a, let's say, velocity of 25 feet per second downward, and then after it travels, let's say 50 feet, we have a final velocity of 0 when it stops, and this occurs over a distance of 50 feet. Again, because the acceleration or deceleration in this case is constant, I can use the equation for constant acceleration recalled from kinematics. V squared equals to initial velocity squared plus 2 times acceleration times change in position. So I have 0 for the final velocity. Initial velocity is minus 25 squared. Since I'm squaring it, I ignore the minus sign, plus 2 times A is to be determined, delta S is 50 feet. So doing this numerical calculation, I'll get an acceleration of 6.25 feet per second squared. And you see why we call this deceleration. Motion is downward, acceleration is opposite to it, upward, so we refer to this as a deceleration or negative acceleration, same thing. As far as part B of the problem goes, what I want to do is, like always, draw a free body diagram to identify the forces, then apply the equation of motion in y direction. So let this be the elevator, then I show the weight, 2,000 pounds, 2,000 pounds weight. There's a tension pulling up, let's call that T. So this shows free body diagram of the elevator, and this equals to mass times acceleration. Again, I have unbalanced forces. I choose A in positive direction, ma sub y. Then as far as equation of motion is concerned, let's say net force in y direction is ma sub y. In positive y direction, I have T going up, minus 2,000 going down, equals to the mass, which is weight, divided by 32.2 feet per second squared, times AY. And AY was known, I just found it as 6.25, so let's plug it in. So in this equation, we only have one unknown. To solve for 2,000 plus some other number is going to give me a tension bigger than 2,000. Recall that in static situation, we often had tension to be equal to the weight because there was no motion. Clearly, in dynamic problems, you don't want to make that assumption. Tension is generally speaking not equal to the weight. In this case, it turns out to be 2388.2 pounds.